Good morning, everybody. Hi, welcome. This is Geology of LA with the Community Nature Connection Training Institute. Thanks, everybody, for joining us this morning. We're excited to have you. I'm here with Hannah Sloan, and we're going to be getting started in just a minute or two. As we have people join the webinar, we'd like to invite you to introduce yourselves. Go ahead and use the chat box to let us know your name and where you're joining us from, and if you're affiliated with an organization. We're going to get started in just a minute. So welcome, everybody. For those just joining us, you are here in Geology of LA with the Community Nature Connection Training Institute. And I'm here this morning with Hannah Sloan. We're about to get started. So as everybody joins us this morning for the training, we'd like to welcome you to introduce yourselves. Go ahead and use the chat box. You can type your name and where you're joining us from. And then if you're affiliated with an organization, we love to know who all is here this morning. So my name is Celeste Gasparic. I'm the Training Institute Manager with Community Nature Connection, and I've been leading these online trainings, hosting them since March. And Community Nature Connection, if you're not familiar, we are a nonprofit organization based in Los Angeles, and our mission is to connect diverse communities to the outdoors, working in partnership with those communities we serve. And the Training Institute is one of our initiatives to increase access to outdoor training opportunities. So we've had a variety of different topics, all relating to the outdoors to increase access to knowledge around the outdoor field. So very excited to have everybody joining us this morning. If you're just joining, go ahead and type your intro into the chat box, your name and where you're joining us from. And if you're affiliated with an organization, we'd love to hear it. And at this time, I'm very excited to turn it over to Hannah Sloan, who's gonna get us started with the Geology of LA training today.
Awesome, thank you so much. Welcome everybody, I'm super excited to be here. As she mentioned, my name is Hannah Sloan. I am originally from Indiana. I moved here for grad school, so I got my bachelor's at Indiana University. I attended California State University Northridge for my master's. My research is on stratigraphy, so I look at patterns of rocks, and I do that out in the Mojave Desert, which is really fun. I've been fortunate enough to intern with the United States Geological Survey. I worked at the Indiana Geological Survey, and I currently work in consulting with a firm out here in California. And I've been fortunate enough to do geologic field work all across the country. I did a lot of my research in undergrad on the East Coast, which is one of the reasons I felt compelled to come out here to the West Coast. I wanted to get everything covered. So that's a little bit about me. Here I am in Glacier National Park eating pizza on one of my breaks. Normally I have a lot more gear, but I took the gear off because lunchtime. So let's get started. So what is...
Sorry to interrupt. I forgot to mention that we will be taking questions throughout the training. We're gonna pause about halfway and I'll go through your questions, so you can type your questions as they arise in the Q&A box, and we'll answer them halfway through the training, and then again we'll have a Q&A session at the end. So thanks.
Thank you for that. So we're talking about geology, and in order to do that, I felt like we needed to know what geology is. A lot of people think geology is just rocks, so just like picking up rocks and naming them and putting them down, and that's geology. And in the most basic sense it is. So as you can see here, geo is rooted from the word earth, and then ology is the study. So in its most basic sense, geology is the study of earth, but it's also the study of earth and its systems. So Geologists do atmospheric science, hydrosphere, so anything to do with water. Water is a big part of geology. My undergrad research was in water chemistry. The cryosphere, and cryosphere is just a fancy word for all the ice on the planet. So glaciers and ice is actually a crystal. And so ice is a really good thing that we can use to study geologic processes quickly. And then solid earth is what people typically think about. So superficial and deep earth being like geophysics and earthquakes, and then just identifying rocks and making maps. So that would be like what you traditionally think about. But geologists also do a lot with the biosphere. So soils, fossils, and geomorphology is just a fancy way to like talk about how the earth moves. So landslides and stuff would be considered more geomorphology. But I have a good friend who's getting his master's in geology, and he does radiation found in tree rings out here in California. So we really do it all. We touch on all aspects of the earth. And so it's a really, really fun science to get into, just because it's all a system that is connected, and I really like it. So if you don't know, rocks and minerals are different. And if you don't know, this is California state mineral, this is California state rock. But what is the difference? A mineral is naturally occurring, inorganic, an element or compound, has an orderly internal structure. So that's just a way of saying that when the atoms line up, they line up in a specific way. And atoms are what make up everything. And so in order to get a specific mineral, those have to be in a specific order. And a characteristic chemical composition, crystal form, and physical properties. Again, that's just saying you need specific atoms to line up in a specific way in order to get a mineral. Rocks have a much kind of looser definition. So rock is an aggregate of one or more minerals. That just means a rock is composed of multiple minerals. And this can be in a few different forms that we're going to talk about on the next slide. And it's just a body of or it can be a body of undifferentiated mineral matter. And again, we're going to get into more of the specifics on the next slide. And again, here's the California state mineral. It's gold. The California state rock is serpentinite. It's a metamorphic rock, which is really neat. It's green. You can find it up north. It's pretty common in the Santa Barbara area. So now we're going to get into our rock types. There are three rock types: igneous, sedimentary, and metamorphic. California has a lot of all three because a lot's happened in California, and Los Angeles and Franklin Canyon have all three, which is really exciting. Igneous rocks form from magma or lava. They have a crystalline structure, usually, and they can form either intrusively, which means that they're formed in the earth, and those are pretty distinguishable by the size of the crystals. So each of these colors in this rock are crystals. Can you see my mouse? Okay, I'm just gonna think yes. Or they can form extrusively, which have very small or non-existent crystals, and those are what we form from lava. Sedimentary rocks are just formed from pieces of broken rocks, which we call clasts, or they can form through chemical precipitation. And chemical precipitation is just a process when, as water is going through places, if there's a lot of ions, so a lot of one particular like dissolved thing in the water, that can start to precipitate or form as a crystal on whatever surface it's flowing through. So one thing that we can use to think about this would be like salt crystals as they form. And sedimentary rocks can form from pieces of any of the three rock types. So you can get sedimentary rocks that form from other sedimentary rocks. You can get sedimentary rocks that form from igneous, and you can also get sedimentary rocks that form from metamorphic. So metamorphic, those are rocks that form from either sedimentary or igneous rocks. They can be more metamorphosed from metamorphic rocks, but they would still just be metamorphic. These are rocks that form from high pressure or high temperature, but it is usually a combination of both. You find those a lot in fault areas and mountain areas where the rocks have been either really compressed or gone through a lot of intense change. And so some of the really common ones that we have out here are slate and marble and quartzite. And those, again, are just rocks that form from the other rock types. So slate forms from shale, which we have here. Quartzite just forms from a sandstone, which is just sand that has been turned into a rock. And marble just forms from limestone, which is a chemical precipitation of calcium from creatures in the ocean. So here's the rock cycle. As you can see, it's not a perfect circle. It is all connected, and there's a lot of going back and forth between the two. So you can get an igneous rock that goes straight to metamorphic, or you can break that rock down. We call that weathering and erosion. It can then be transported or moved, and then you get deposition, where it then can be turned into a rock. And then you can go back, you can make that metamorphic, or you can weather that even more, but it all eventually will go back into the earth and be recycled. It's just on a very, very, very long time scale. So this is the rock cycle. If you want a video that explains it a lot better, we don't have time to really break it down today. This YouTube video is a great link, and I know that Celeste is going to be sending out this PowerPoint, which has all the references, and I think she's going to be sending out some specific references separately as well. So in order to talk about mountains, we got to talk about faults. And lucky for us, California has, and Los Angeles has experienced all three. So we have normal faulting, and that's from extension, or when the earth is pulling itself apart, one side would fall. We don't have necessarily like a lot of that happening currently, but there is some of that. So that would be normal faulting. And then we have reverse or thrust faulting, and that's when pieces of the earth are going together. So then one would want to go over the other, and that causes faulting and causes earthquakes as well. And then strike slip is the one that anybody in California is probably most familiar with, and that's just when the rocks are going side by side, and we would like them to just be able to glide side by side, but rocks are very rigid, and there's a lot of imperfections there. So when they move, as we all know, they cause shaking and they cause earthquakes. But as we all know, again, the earth is a round object. And so typically, even when there's strike slip faulting, there's a slight component or amount of one of the other two types of faults, because again, you have to make up for the roundness of the earth, and you have to make up for that space that's being moved. Okay, that was kind of a lot to start with. I'm wondering if there are questions. Some of you might recognize this Peanuts comic. We love it.
If anybody has questions right now, or if they come up at any point throughout the presentation, just go ahead and type them into the Q&A box, and I'll be monitoring those and giving those to Hannah throughout the presentation. None yet, Hannah.
None. Oh, there might be one.
Oh, we have one. Oh, what kind of fault is a subduction zone?
Yeah, so a subduction zone you can think of in kind of the same way as a normal fault, because it is two rocks going together. So one is going over the other. It's a compressional feature, which is really the main thing that we use to distinguish the faults. So in the most basic sense, a subduction zone would be a normal fault.
Cool. Why are the fault types important to know?
Yeah, so fault types, especially in California, have really shaped the landscape, and the Santa Monicas have experienced all three. I'm going to show you guys a timeline in a little bit, a couple slides away, that takes us through what different fault types were happening at one point in the Santa Monicas. But they're really important to know if you're curious about why the landscape looks the way that it looks. And they're also just good to know because certain fault types, so subduction zones, which we've just talked about, have the highest magnitude earthquakes typically. So if you are curious about maybe predicting some failures or predicting stability for development. They're just a good thing to kind of keep an eye on. Earthquakes are fun but scary, so they're just kind of a good thing to know.
Awesome. And then any idea why serpentine was chosen as the California state rock?
Yeah, so serpentinite is actually really, it's really like, it's really rare, and it's pretty common in California because it requires a certain, we call them, um, it requires a certain rock to exist before you can get serpentinite, because you have to have a specific mineral assemblage, which we talked about a little bit earlier. So serpentinite is not really found in too many other places in the United States, and the fact that it's so common out here just makes it a really unique California thing. And I think that typically when they're choosing, I've never been a part of the community to choose like a state flower, state bird, state anything, but I think they typically want it to be unique and prevalent and common to the state that it's in.
Great. Thank you. We have one more question that came in through the chat box. In regards to the rock cycle, metamorphic rock can be both of the other types of rock. So then would all rock be metamorphic, or how would you describe the interrelation of the three?
Yeah, so sorry if that was kind of confusing. I might have gone through that a little bit too quickly. So metamorphic rocks can be formed from the other two rock types. So metamorphic rocks are their own thing, and then sedimentary and igneous rocks are also their own thing. They're all three separate rock types. So metamorphic rocks can be formed from the other two rock types, but as soon as they become a metamorphic rock, they're no longer a sedimentary or igneous rock. As soon as the rock changes rock type or goes through the cycle, it then gets put into a different category. I'm hoping I cleared things up a little bit better. Thank you for these questions.
Yes. Awesome. Thanks. That's all the questions for now. But like I said, as they come up, just type them in the Q&A box.
Okay, so now we're going to talk about the Santa Monica Mountains specifically. So if you do not know, the Santa Monica Mountains are about 46 miles long and 8 miles wide. So it's a fairly significant mountain range, at least in California, right? It's part of the transverse ranges, and it runs mostly east and west. When they were formed running north and south, but there's been some fault action that has since rotated them. And there's an estimated of 1,040,089 meters of fault segment that cuts through the Santa Monica Mountains. So there's not an insignificant amount of faults, but not all of those faults are necessarily currently active. And then fossils are very prevalent throughout the Santa Monica Mountains, and with the most abundant being invertebrates. So these fossils, as you can see, there's a picture. That's the fossil dating chart from the USGS. So some of these fossils can be found in the Santa Monicas. I don't know if all of them can be found in the Santa Monicas. One of the cool things about fossils, though, is we have a pretty good idea of what fossils were around during what time. So we can use this to do something that we call relative age dating. And relative age dating is just a fancy way of saying we don't know exactly how old it is, but we have this piece of the puzzle. So then we can say that it's at least between this date and this date. So this is a little chart that is used by the USGS. And again, you might be able to find some invertebrates. And I talked to Celeste this morning. There are, if you're in the Nature Center, there is a section for geology where they have some fossils on display that have been found in the Santa Monica Mountains. So yeah, fossils. So this is the timeline that I was talking about. So the Santa Monica Mountains have actually experienced all three, and this timeline is mostly to scale. The mountain formation is kind of maybe slightly bigger than it should be, but the timeline here is pretty much to scale. And a little caveat about this, I used the National Park Service geologic report that was done in 2015 to get all of these times. So this was data that was collected by, I think, both the USGS and the National Park Service. When you Google when the Santa Monica Mountains were formed, you can get some slightly different ages. And I think that has a lot to do with the age of the rocks and not necessarily the age of when the mountains started coming up. So there is some discrepancy on the internet, and so this was all taken from the National Park Service Geologic Report. If any of you guys are Googling as I'm doing this. So that would be an explanation for that. So as you can see here, I know somebody asked about subduction earlier, which would be, again, just like a compressional and reverse or, yeah, fault. And so this part actually formed a lot of the rocks that needed to exist to make the mountains, because in order to make mountains, there has to be something there to push up. So a lot of the history of the Santa Monica Mountains was just putting those rocks in place in order to be uplifted. So the Farallon plate, which is just the plate that was out in the ocean, was going beneath the North American plate during this time. And so that formed all three of the rock types because we were shallow ocean at that time. And then we went into a brief period. There's a transitional period from subduction to getting strike slip, which again is when the rocks go side by side, where the Los Angeles area experienced normal faulting or extension, so of being kind of pulled apart. And this allowed for a lot of intrusions, and that's just a fancy word for something coming into an area that's already there and kind of making its home between pre-existing rocks. So that allowed for a lot of volcanic intrusions. And during this time, we were getting igneous because of those intrusions and sedimentary rocks. And then finally, about 4 million years ago, which is super, super short geologically, I couldn't believe how young these mountains were. Like I mentioned, I did a lot of work on the East Coast. The Appalachians are about 480 million years old, and the Sierra Nevadas are about 40 million years old for reference. So when I saw that the uplift of the mountain started about 4 million years ago, my mind was kind of blown. And the uplift was about 4 million to 3 million years long. And if you're wondering how we're able to kind of estimate that timeline, again, we use the rock types that are there, and then we can use more, they're called absolute dating techniques, where we examine certain particles or features of the rocks, and we can really narrow down what times things were happening. And when the mountains were at their highest, it is estimated that they were over 10,000 feet high, which is very high. And that is obviously significantly higher than the highest peak we have today, which is only about 3,111 feet high, and that is Sandstone Peak. And if you're wondering how we can guess how tall they were, or estimate, is that a word? We can use the different rock types to narrow down, or we can look at different features. So rocks take on certain patterns when they undergo certain pressure and temperature conditions. And so we can use those as kind of keys to unlock maybe how tall they were, because obviously if there's a lot more rock on top of a rock, it's going to be hotter, it's going to be more confined, it's going to do some different stuff than what we see just being deposited or being laid down today, like in a river channel. So there's a lot of clues that we use as geologists to kind of put together these puzzle pieces to answer all these questions. But since none of us were there, we have very, very, very strong evidence to support 10,000 feet, but maybe there are 10,500 feet. There might be some slight wiggle room there. So if you've not seen the geology of the Santa Monica Mountains, I know this figure is a little bit hard to see, especially in the geologic units. I'll be zooming in on this red square on the eastern side of the map here. That is where Franklin Canyon Park is. And so these are all the geologic units of the Santa Monica Mountains. It's a really good figure, and you can get that through the National Park website when you go to the Santa Monica Mountain specific page. And the gray is for recent sediments. One thing to kind of safely assume is that there's going to be rock that's being deposited everywhere right now, for just for simplicity's sake, but it's not necessarily something that they felt the need to map or that was an important mappable unit. Um, so if you're hiking along and you're like, that rock probably isn't a billion years old, you could be right. And just because it's not on the map doesn't mean that there's not recent sediment where you are. Franklin Canyon Park. I know we have some volunteers from Franklin Canyon Park, so now we're going to get a little bit more specific to the park itself. So like I said, we're going to be zooming in on that square. This is the same red square that I had in the previous slide. And as you're looking at this, you might notice that there is this little squiggle on the timeline. Again, this timeline is pretty much to scale. This little squiggle is what we in geology call an unconformity. And that's just a fancy word for there's either no rock that was deposited during that time, so there wasn't any action at that time, or there was rock there at one point and it got taken away through erosion or breakdown. So that's just a way that we show that there's some missing information right there. So these are all of the primary units that you can see in Franklin Canyon. You can see here we have metamorphic down at the bottom with the Santa Monica Formation. And I'm going to show you guys some pictures of these rock types in a little bit. They won't necessarily be from the park because of COVID. I wasn't able to get out there myself and hike around, but I have some good example photos that you guys can use as you hike to maybe get an idea of where you might be. Then we have igneous rocks. We have igneous down at the bottom here, and then again at the middle. We talked about that time of extension when there was intrusions that were happening. And then we have a lot of sedimentary rocks, and these are where you're going to most likely find, these are going to be where you find fossils. If you find fossils, I'm not saying that fossils exist in all of these formations, but you might. And then I have the Monterey here, and then I have oil in parentheses. So the Monterey Shale is the rock that a lot of people, that's related with oil in California. There's obviously other formations that have oil, but the Monterey Shale is like the big grab one that a lot of people pay a lot of attention to. And that doesn't mean there's oil in Franklin Canyon Park or anything like that, but I just like to have that reference there so you guys can kind of have an idea of the rock units in California. And then I guess I should explain formation. Sorry about that. A formation is just a word that groups specific rock units together during a specific time, and they're typically grouped together based on relationship to one another, or if there is a significant event in geologic time. So the volcanics were obviously a significant event that separated the deposition of these other two units that are the other formations. And so that's just a way that we group rocks to kind of block out chunks of important geologic time. So what do the rocks look like? And again, these aren't necessarily taken from Franklin Canyon Park, and the rocks can look different. They are not all necessarily going to look like this because they experience different things at different places. But these are pretty good pictures to use as somewhat of a reference. On the far left here, we have the Santa Monica Formation, which if you remember, is that metamorphic, really old rock. So one of the ways that you can maybe start to tell if it's the Santa Monica Formation would be how kind of broken up and chewed up it looks. It's gone under a lot. It could have a lot of cracking through it. But again, these are distinguishing features that you could find in other rock types as well. The dark color can also be a really good indicator of the Santa Monica Formation. So as you're hiking along and you maybe start to see rocks that look like this, you might think maybe I'm in the Santa Monica Formation, and then go to your geologic map from the lovely National Park Service to cross-check that. And then we have Cretaceous igneous granite. And this is in geology what we would call a hand sample, and the other two here would be called outcrops. So a hand sample is really just anything you can pick up and hold in your hand, and an outcrop would be a body of rock in place. Um, so this would just be something that you can see, and one of the ways that you can start to tell your igneous granites and your granites, a lot of the crystals and the minerals in the rock take on a square shape. Um, they form as a square because remember we talked minerals have a specific kind of internal structure. And so there's a few specific igneous minerals that form as squares. So if you pick up a rock and it looks pretty blocky and it doesn't look like it's been altered, then you can think, hey, maybe I'm looking at some igneous granite. And again, always just cross-checking with your geologic map. The Chatsworth Formation is where we start to get into some of the sedimentary rocks. So the Chatsworth Formation is a sandstone. And a sandstone is just sand that has been turned into a rock through compaction or through what we call liquefaction, which just means that it's cemented together through chemicals. And a lot of times the rocks are either named after an area or an area is named after rocks. So if you're thinking like, hey, Santa Monica and Chatsworth are places, typically the people who name them try to name them with a very distinguishing name that also helps you kind of understand where you are in the world. So it's kind of helpful. And then the Santa Susana Formation is also a sandstone. And again, because of sedimentary rocks are deposited through some different processes, it's not always going to look like this. There could be portions where you have bigger clasts or pieces of broken rock that were deposited in like a specific part of a river, or you could have different like beach deposits. Because the earth is big and the formations were laid down over big stretches of land, they're not necessarily always going to look the same in every place. And as you're hiking along, it might be hard to distinguish the different sedimentary units. It'd be pretty hard to tell Santa Susana versus Chatsworth Formation. But you can kind of get an idea of where you are geologically if you're thinking maybe I'm in Santa Susana, maybe I'm in Chatsworth. And then we have the Topanga Formation right here, which is a little bit oranger in this photo. And that would just be the differences in color are just based on the differences in what rocks are making them up. So what chemicals exist in the rocks define the colors, right? And then if you look closely in the Topanga here, you can kind of see what I'm talking about with how the rocks can be different and have different sizes of rocks in them. There are some bigger in the middle of this middle rock. There are some bigger pieces or class of rocks that were maybe deposited when the water was flowing a little bit faster and could pick up those bigger rocks. And so those were turned into rocks, and we use those as geologists to kind of, again, re-evaluate and figure out the pieces to the puzzle of what happened in this area during that time. The Conejo volcanics are kind of hard to tell against the Santa Monica metamorphic unit, but the Conejo volcanics typically have these white circular units in them. And so they're pretty well defined by this kind of darker black body, and then you can get these like white units, and those are again different colors because they're different chemicals inside of them. So as rocks cool and crystallize, they cool and crystallize at different times based on what's making up that rock. So the outer rocks cooled and crystallized, and then these white rocks cooled and crystallized, so you get this cool pattern on the Conejo volcanic. And then the Monterey Formation right here, again, I mentioned that this one's the one that's kind of important for oil production in California. And that one, the shale, is typically very distinguished by its thin layers, and it's pretty crumbly. So if we have any rock climbers out there, you know that you'd want to climb the Santa Susana or the Topanga Formation and not the Monterey Shale, because you wouldn't be able to keep going up it. You would just kind of crumble and break off, and it'd be very unsafe. So again, these are just photos that you can use as you're hiking along. You can look at the rocks and maybe start to think, maybe I'm in this unit, maybe I'm in that unit, and then compare with your geologic map to confirm, which is pretty fun. So Franklin Canyon specifically, I have the word canyon bolded a bunch because Franklin Canyon is a canyon. One of the ways that geologists use to kind of tell what's happened to form something would be the shape of the earth. And one of the indicators of the canyon being carved out by water is this really sharp V shape, because if you think about how water flows, it kind of cuts, it keeps wanting to cut down in between the rock, and so you get this nice V. And as you're hiking along in Franklin Canyon, you can kind of see some of those happening in modern times, which is really fun. And then just a little bit of information about where the word canyon comes from. Yeah. So this is a rock that's called Geology rock that's in Franklin Canyon Park. I'm not sure the significance because it does look like any other rock, but it's a fun little place if you want to stop. I kind of highlighted here some different layers that you can see in the rocks. So sedimentary rocks, we typically think of them as layers. And as you can see here, the layers have been tilted. So in geology, we assume that all of these rocks were deposited flat. And then any motion or any angle that has happened was something that happened after the rocks were deposited. So we don't assume they were deposited at the angle. We assume that that happened later through various processes. So you can see here, if you look where my red line is, just right above the bottom one, you can start to maybe pick out some of those layers. One of the fun things that I do in my field work, because it is honestly one of the best ways to kind of figure out what's going on, is to just find a layer in your rock, and if you can physically touch it, it's really ideal, and just hold your finger there and walk along it. And if that layer disappears or is cut or is anything happened to it, then we know that something happened after that layer was deposited, whether it be a fault or a river cut through or just got taken away over time. We can start to use those little clues to help start to build together the pieces of the puzzle, which is what I do in my research. So I think it's super fun, and as you can see here, there's a few fairly distinguished layers in this rock. But again, it's always best just assuming you look for poison oak out here, poison oak, and make sure that there's none growing on the side of your rock. It's a really fun thing to do, to just kind of get your finger on it and follow the layers and try to look in the layers and try to find fossils. And yeah. So that's the end. Again, these are all the references I used. If you're wondering which reference goes to what specific piece of information or what figure, I put in parentheses the name of the place that I got the reference, and then I put in bold the number that is the number of the reference on the side. And the two that are in bold, this one being the National Park Service geology report that was done, I said 2015. It was, I guess, published in 2016. So this one's a really good one to have. And then this one is just the information on the National Park Service website about the Santa Monica Mountains. But all of these are really, really good references to go and look at. Yeah, that is the end. Thank you all for coming. And
we have a bunch of questions for you, Hannah. Are you ready?
Wonderful. I hope I can answer them.
So it sounds like water was the most likely cause of erosion for Franklin Canyon. We have the slide showing the V shape. But what about for the Santa Monica Mountains? Is water the most likely cause of erosion?
So there could be I don't know specifically, and I definitely don't want to overstate my level of understanding. But I would say that most likely water would be a significant source of erosion through the Santa Monica Mountains. Again, it would just be kind of based on the shape of where you're at. there could also be wind is always eroding. They could be less high because of, we call it isostasy. So the whole like crust, which is just the top layer of Earth, um, kind of kind of floats, for lack of better terms. So there could have also been some movement up and down based on that. Again, I'm not super familiar. I think for the main like canyons and valleys that you see, water is the safest assumption through the park.
Cool. Let's see. We had a question, I think, going back to the slide where you were showing rock types. Is that sandstone around the Cretaceous, sorry, this has a lot of words. Is that sandstone around this Cretaceous igneous granite?
So I was not there. I did not take that photo. So I cannot say for a fact. I think it is fairly safe to assume that that rock was taken in an area where there's a lot of bits of the igneous granite. So sedimentary rocks aren't always sandstones. That's just kind of what we have the most of. So if those rocks were to if those pieces were to turn into rocks right now, they'd be too big to be called sandstone. So then we would move into other rock classification types of like cobble, or like the shale is a finer version. So there's different levels. And again, I was not there. It looks like it might be on some modern deposits, which are called alluvium. So I'm not sure.
So why, excuse me, why would we assume that the rocks are deposited in flat layers?
Yeah. One of the great question. I'm trying to like think about how I want to answer it. So we assume that rocks are deposited flat because that's the easiest way for them to stay in place. So there are deposits on slope, but it is fair to assume that over time that those would be either eroded away or moved. They don't necessarily always liquefy, and typically it's not always going to be perfectly flat, but typically there are some curves. There's some slight like variation in earth levels, but typically when you have big stretched out formations like that, it's fair to assume that at the time of deposition they were deposited in a mostly flat environment, because that's the environment and the energy that allows them to take the time that they need to turn into rocks.
Cool. Let's see. Are metamorphic rocks usually the oldest dated rocks?
I mean, any rock can be metamorphic. So some of the sedimentary units are probably somewhat metamorphosed, which is not something I probably should say. But any rock can be metamorphic. So you can get a young sedimentary deposit or a young igneous intrusion or a young igneous formation. And all that you need to do to make it metamorphic is to put it under some pressure and heat, a lot of pressure and heat. So it's not necessarily an age indicator as much as it is an environmental indicator of what the rock has gone through. So in this particular unit, they are the oldest, but that wouldn't always necessarily be the case. In mountains, they can be too, just because they're at the very bottom, right? But again, that's not always the case, because all you need to do is to heat those rocks up or push on them a lot, and you can start to get metamorphism. So it's not an age indicator.
Awesome. Let's see. Are all of the canyons in the area, Topanga, Laurel Canyon, carved out by water?
I don't know the answer specifically. I would say that it's maybe safe to assume that, but again, I don't know the answer specifically. I know in the first reference that I have, there's a lot more specific information on what the Santa Monica Mountains have undergone since formation. So that would be a good reference to look at that. But if they have that really sharp V shape that we see really nicely in Franklin Canyon, again, it's fairly safe to assume that they are.
What other things would have carved out the canyon? What are the other possibilities?
Really, the only other major like canyon carver, if there was high wind that was trapped in a certain place for a very long time. But the other thing that we use when we think about canyons is glacial, which I feel very safe to say it's not glacial. And those make U-shaped valleys because the ice can carve rocks so easily. So V versus U is what we use to determine ice versus water. But again, I'm not sure. There might be some places in the Santa Monica Mountains. There's definitely that carving in the Sierra Nevadas. I don't think there is in the Santa Monicas though.
Cool. Let's see. Oh, this is a interesting question. So why are the Santa Monica Mountains now only 3,000 feet plus when it was over 10,000 feet at one point?
Yeah. So in geology, we think about potential energy a lot, and I don't know who took physics or what you remember, but potential energy is just the potential for something to do something. And so if you think about how much easier it is for the earth to break down rocks that are sticking out and standing up versus in like holes, it's a lot easier to move that rock, and there's a lot more that the rock experiences. And so through time, the mountain formation again lasted about 1 million years. And so it's been about 3 million years, which is not an insignificant amount of time. You can get a lot of breakdown of that rock through various processes. Or plant roots break down rock, animals digging break down rocks, water breaks down rocks, wind breaks down rocks, and there's just a lot that's happened over 3 million years that could break down rocks. Again, there could have also been some response based on weight because mountains weigh a lot. So there could have been some response, but I'm not sure if that happened in the Santa Monicas.
Great. Let's see. How do rock formations impact plant communities?
I love this question because I think it's a really good question, especially if you're driving along in California or anywhere. You might notice that there's an area that looks like it's mostly the same, but you have very distinguished plants in like one part and not the other part. So when I'm doing mapping with like old photos, I've done some mapping with photos from like the 1950s. One of the best ways to distinguish different rock layers or units is by looking at what plants can grow where. So as we talked about, rocks are made up of minerals and they're made up of chemicals. So different rocks provide different chemicals and plants need certain chemicals to grow. The rock hardness and strength can also impact it. Plant roots can cut through rock, but the rocks that are weaker typically allow more easier growth of different plant types. So rocks and plants actually have a very close relationship. There have been like legal cases of like landslides against like people that are cutting down trees. People saying like that landslide would not have happened had you not cut down those trees. So plants also stabilize rock as much as they tear them down. They can hold the rocks in place. You hear that a lot with like rivers too, how you can stabilize riverbanks with plants and trees. So it's a very close knit relationship. But yeah, one of the fun things to do is to see an area and see like right next to each other on like fairly flat land, so there's no altitude. Controlling the plants is how you can go from one like grass type to another grass type just based on what rock you're in. I think it's super fun.
That's awesome. Do you have any idea or like any estimate on how old is that geology rock at Franklin Canyon?
I wasn't able to go there. And so I really don't. It looks sedimentary, but I really don't know what formation it would be a part of. Um, I was not able to go to the park because of COVID. And things being closed down in my schedule and all sorts of fun stuff. So I'm not sure.
Because we had, another question come in, and I know you weren't able to visit Franklin Canyon, but from your research on the area, can you think of any like tips or like fun facts that would be valuable to share with youth who are visiting the canyon?
Yeah, I think if you're wanting to think about geology specifically, there's a lot of activities for kids to help them kind of think about geologic time. Because again, if we go back to the timeline, um, where'd she go? Did I pass her? I might have passed her. Oh, it was back in the Santa Monica's. Um, it's a lot of time. 156 million years is fairly significant. So that's one thing that I have done with kids in the past. Again, I think just hiking along and identifying those layers that you can see. Sorry, I'm clicking so rapidly. And looking at the layers that you can start to find from sedimentary rocks is really fun. You might be able to find fossils. So maybe the Nature Center has more information about fossil localities, or you can find some naturalists that are a little bit more familiar to maybe find fossils. Again, I wasn't able to go. And then, just picking up rocks and kind of just feeling them and talking about the different rock types. Since there's all three in Franklin Canyon Park, it's pretty fun to kind of start to feel the difference in how the rocks feel and what they do.
Awesome. Let's see, are there beneficial relationships between, you kind of touched on this, but are there beneficial relationships between rocks and flora and or fauna?
Yeah, for sure. I mean, a lot of animals use naturally formed caves as homes. Um, and there's a specific bird type that I know exists in Montana, and probably there's some out here that make their nests in a certain rock type that kind of they can get into. And I think there's just kind of a symbiotic relationship between everything on the planet, which is again what was the driving factor for me to become a geologist. And so I think since it's all one interconnected system, there is that relationship. And I mean, the rock types can have somewhat of control on what grows there. So I don't know how much you guys know about like things that are happening globally with geology, but Brazil is having a lot of trouble with their soil, and so there's no plants there, and thus no animals there. So it's all definitely very interconnected, and there are things that we can do to keep the rocks healthy, for lack of better terms, to continue having that growth and having that wildlife.
Great. So we mentioned wind and water and ice all as different ways that canyons are formed. There's a question, could faults cause canyons?
Yeah, they can cause the earth to separate. So they can definitely cause something similar to a canyon. They can extend, and you can get drops in the earth. But as far as these canyons specifically, I wouldn't say that that's what caused them. But you can definitely get breakdown of rock and canyon-looking features with faults.
Great. Do you know how old are most of the rocks in California, or what is the range?
There's like from millions of years, billions of years to now.
Wow.
There's a lot, yeah. I mean, I feel like, the oldest rock in California is at least 1 billion years old. I should have looked that up and double checked it before I came here. I want to say 1.2, but don't hold me to that. So yeah, there's really any variation of rock. As far as most rocks in California, I don't know if there's necessarily a way to quantify like the average, or if you'd want to, because it's very specific to the area. So certain areas have certain age rocks that other areas don't have. So it's really just based on what area you're in. They're very old to very young.
Awesome. Let's see. Oh, this is a cool question. I've never conceptualized anything like this. How much do the mountains weigh?
Oh, no, a lot. Yeah, I don't know. Enough to where there is response for miles away. And when I say response, there's flexure or trying to think of very like non-technical words. There's the earth kind of curves and changes for miles outside of mountains because of the weight of the mountains. So I do not know how much they weigh, but we can assume that they weigh a significant amount.
Yeah, enough to affect.
Enough to bend the earth.
Yeah, whoa, that's awesome. Very cool. Let's see. So I think this question is referring specifically to in Franklin, when it rains, parts of the trail get really muddy, like clay-like, that like is sticky and it builds up and it sticks on your shoes. But then other places, it's like gets porous, so the water is like going into the earth. What is the relationship between the rocks and then like the type of dirt or the type of surface that you're hiking on?
Yeah, so there's definitely like a direct relationship there. So when rocks break down, they need to be moved. And so if you're finding areas that are more muddy versus not, that could be a factor of what's moving it, or it could just be what's there to be broken down. So mud is like super, super, super fine pieces of rock. And so if you have that specific mineral and rock type in that area, and that rock is being broken down and left in a specific area, then you can start to get a lot of mud, to where if you have, you don't have a lot of that mineral type in a different area. If you have just like a sandstone and that sandstone breaks down, it's not necessarily going to make mud quickly. And so you're not necessarily going to get that same mud. And so it could be a factor of transport again. And so that is just, it's easier to move certain rocks than it is to move other. Mud is fairly light and can be moved quicker. So it might just be an area where there's lower energy, where the energy kind of all dies in that spot. And so you get just all of everything that was left is just the mud. Or it could be a factor of what rocks are there and being actively broken down where the mud is. So there's two scenarios, and they're probably honestly connected pretty heavily.
Awesome. So we have time for like this last question that's come in. And then if anybody has like other questions that have come up that didn't get answered, please reach out to the training at Community Nature Connection. I can connect you with Hannah. We can give you more information and resources that's all coming in the follow-up email. But we'll end with this question. Do you know, Hannah, of any good trails to find fossils on in the Santa Monica?
No. But I know that there are a lot of resources. Yeah, I do a lot of hiking, but I haven't necessarily found specific places around here that have fossils. Yeah, I typically hike for the big features and not like specific rock types. So I personally have not done very much research into that. And again, I haven't been to Franklin Canyon, so I wasn't able to hike around and maybe find fossils. But I know that there's a lot of resources dedicated to geology and fossil finding. So I think it's just a quick Google search away.
Yeah, and a couple of suggestions are coming in through the chat. Red Rock Canyon. There's actually a trail called the Fossil Trail that's off of the Topanga Lookout Trail. So I bet you Google search might help answer that question as for finding fossils in the local mountains. Um, so great. Well, I want to thank you so much, Hannah, for the webinar today, for being here and giving us all this awesome information, getting us more familiar with all the rocks and geology in our area. I want to remind everybody that I'll send a follow-up email with resources, with the recording to this training, and then also some of the, oh yeah, I said resources. So great. Thank you everybody so much for being here, and thank you to Hannah. And that does it for us this morning. All righty. Bye.